Hello, my name is Jonas Gutknecht from the Zurich University of Applied Sciences, and with this presentation I would like to give you a short insight into our paper Multilayer ToF Comparison of Different Multipath Resolve Methods for Indirect 3D Time-of-Flight. Indirect time-of-flight is a method to measure the three-dimensional scene. For this purpose, the scene in the field of view is illuminated with infrared light with a known modulation frequency. This light is reflected by the objects in the field of view and thrown back to the 3D camera. The camera now measures the amplitude and the phase difference of these signals for each pixel. With known modulation frequency and speed of light, the object distance can then be calculated. However, in many real applications, light is reflected not only via one but several signal paths. This can be caused by sharp edges, transparent objects, or scattered light. In this example, the two dashed reflection signal from different signal paths overlap to form the gray solid signal. The phase and amplitude of this signal does not correspond to any real signal path, and thus results in considerable measurement errors. In this project, three different methods for separating the individual signal paths in the case of multipath interference were compared. All three methods require multiple measurements with different modulation frequencies. In the first method, the problem can be modeled and solved with a closed-form formula. This approach is already known in the literature. A second method is based on the Orthogonal Matching Pursuit algorithm, which approximates the measurement signal in an iterative process with a linear combination of individual entries of a dictionary. This method is also described in literature. In the third method, the particle swarm optimization method is applied to the problem, which, to the best of our knowledge, has not yet been described in literature. The solution space is iteratively searched for the global optimum with a large number of particles. The behavior of the individual particles is modeled on the swarm behavior known in nature. The results of a benchmark measurement with a plastic grid at 2.4 meters in the front of a white wall at 8 meters are shown in the figures, at the top as 3D point cloud and at the bottom as distance histogram. On the left side you see the measurement results without multipath separation for a single modulation frequency. On the right side there are the results of the three different separation methods. Without separation, none of the real distances were measured correctly. The measured distances are in the range between 5 and 7.5 meters. With the three separation methods, however, the two discrete distances of the grid and the wall are clearly visible. While the closed form and the PSO method have some distance noise, the OMP has produced the most reliable results in the real measurements. A disadvantage of the OMP method is that the relatively high distance difference between the signal paths are required for reliable separation. Assuming an identical signal amplitude of the reflections, the minimum distance difference for separation can be calculated, which is for our setup for about 2.7 meters. According to our findings, this limitation has not been described in literature so far. With all tested methods, the error caused by multipath interference could be reduced by more than 90%. While the closed form method is sensitive to measurement errors, the PSO method is CPU intensive and results in high distance noise. The OMP method achieves the most reliable results for the tested sceneries. Thank you very much for listening. For more detailed information, you can find a video of the project on YouTube or visit me at the IEEE Sensors Conference 2021. Goodbye.